So we are going to welcome Drew Landman. He is a 34-year veteran of the Old Dominion University College of Engineering and Technology. Dr. Landman's career highlights include 13 years as chief engineer at the ODU Langley full-scale wind tunnel in Hampton, Virginia. He was responsible for test design, instrument design and calibration, customer interface, graduate student mentoring, engineering support and review, as well as managing the staff engineers and technicians. That is a lot of stuff. He served as the lead project engineer for many automotive, heavy truck, aircraft, wind turbine, and unmanned aerial system wind tunnel tests. Recent interests are focused on force measurement and statistically defensible experiment design, primarily to support the wind tunnel testing, with sponsorship coming from NASA and the DOD. Dr. Landman has served as a consultant and trainer in the area of statistical engineering to test and evaluation engineers and scientists at AIAA, NASA, Airbus, Ariane, ATA, U.S. Air Force, U.S. Navy, U.S. Marines, and the Institute for Defense Analysis, which is IDA. He is currently co-authoring a text on wind tunnel test techniques and has over 100 published journals and conference papers. So we welcome you. We're excited to hear about your research.
Thank you very much, Sherry. Have I passed the first test? Can you see the slides?
We can see you, we can hear you. Good.
That's excellent. All right, well, let's get started. I'm going to talk today about an I-optimal SplitPlot design, and it is for something that Greg alluded to in his last talk, EVTOL, which stands for Electric Vertical Takeoff and Landing Craft. And we'll be talking about tilt-rotor performance. And if you look at my two pictures there, you see small models of electrically powered multi-bladed rotors, which will be the subject of the talk today, and how we structured experimental designs to characterize the performance of these using design expert software. Okay, so I'm going to give you a practitioner's eye view of SplitPlot experiment design and application to wind tunnel testing. You heard my bio. I came into formal experiment design really out of necessity. And you read back through history and you find out a lot of people got into it that way. And that is that we were working on experiments and we were trying to answer questions clients were asking, and we couldn't answer them with robust mathematical justifications. And so we started looking for ways to do that. So things like uncertainty in calibrations or regression models to support aerodynamic characterization. So hard to change factors are fairly common in wind tunnel testing, and there was a lot of resistance in the beginning when everybody was talking about fully randomized designs. And we still have a lot of resistance, but I'm trying to overcome that more and more now. And we're making good progress, particularly in education of NASA engineers who are now taking courses to learn this if they haven't learned it already. And we're also educating aerospace engineers through the AIAA. So we're making some progress. And in the next 40 minutes, I'm going to review a recent study. I'm going to go through a description of methods and try and feature how we go about this experiment design in design expert software. And I want to acknowledge my student, Michael Stratton, who has just taken a job at Patuxent River in flight test. And he's the one that did most of the heavy lifting in this in terms of running all the experimental runs. And I should also mention some financial support from NASA Langley. So why use tilt rotors, or what are tilt rotors? The picture at the top right shows one version of a tilt rotor craft. Vertical takeoff and landing is what VTOL stands for. The E just means electric powered. And urban air mobility is now a large emerging aviation market. The idea behind urban air mobility is to reduce ground and air traffic congestion, travel times, and emissions. And these craft are going to combine the maneuverability and flexibility during takeoff and landing of a helicopter with the forward flight efficiency of fixed wing airplanes. The electric propulsion systems really decrease the mechanical complexity, which allows more freedom in vehicle designs. So we see all sorts of variants coming out nowadays. And the idea of distributed propulsion, meaning using smaller rotors with many motors around the aircraft, gives us a lot of different aerodynamic benefits, and it's very flexible in how we approach our design. Is it a new idea? Probably not, okay? Here's Nikola Tesla's patent from 1929. He proposed vertical ascent and descent using the same propeller used for forward flight. So it's not a new concept, but it's one that is really come into vogue now that we have efficient electric power and more advanced batteries. At NASA Langley, they're working advanced air mobility using a test bed that they call the Langley Aerodrome 8. Picture right shows the view of that model from the top view in the 12-foot wind tunnel of NASA Langley. So you can see that there are 8 motors and propellers visible there. Their speed is indicated by little n, so n1 through 8. You can see 2 wings that are both tilted. So there are 2 more factors, the wing angle of incidence. And you can see at the trailing edge of the wing, or the side that is white, you can see that there are Greek letter deltas there. They're all control surfaces. So we have a lot of factors here, and we're talking about an aircraft that hasn't seen a lot of historical use. So we don't have a lot of data on this at all. In fact, we have very little. And one of the aircraft that Greg showed in the last talk, the CV-22, is one of the I guess, outliers in that statement, because that's one that's been flying for a long time, but there are very few other examples. So a lot to be learned still about these aircraft. So wind tunnel testing methods provide a rapid means of characterizing the aerodynamic performance, particularly when you have a very complicated geometry like this one. And at NASA Langley, they've been building their test programs on statistical engineering now, using design of experiments and response surface methods. One thing that has been learned from aircraft like this is there are many, many complex interactions, and the models that describe their performance are higher order. So they don't lend themselves well to classical second order designs. You have to think a little bit more like what Greg is showing, and we have to have more points. We have to have design spaces that are constrained in odd ways, right? And yet we still have to look back and say, we're worried about how much correlation is there in our parameters. We're worried about prediction variance and all the metrics that we look at in experiment design. So what's the project motivation? Well, EVTOL technology, as I mentioned, is fairly new. The propeller aerodynamics that are associated with them, in this case, require a propeller incidence, meaning that it's tilted up against the airflow. There's been work done in that, but it's not really well understood. And the newer blades that we're using now in the aircraft and the smaller sizes bring on some additional complications. The overall flight modes that the aircraft sees includes hovering, so flying like a helicopter low to the ground, transitioning to forward flight, and then obtaining forward flight, and then reversing the whole process to land. Analytical modeling is providing relatively poor predictions. It's difficult to build this up from first principles. Computational methods can be used, but they're complex, and with a complex aircraft, they get even more complex. They're arguably not as accurate. I'm sure the CFD people are throwing darts for me saying that, but I think that overall, it's a lot of extra work in order to do it computationally. So wind tunnel experiments are needed to gather specific propeller performance data for simulation. So our project objectives then are performance evaluation for the propellers used on the LA-8 UAM design I showed. Currently, it uses a 3-bladed propeller, but they wanted to look at 3, 4, 5, and 6-blade configurations. They want to look at the full performance envelope for range of RPM, or motor rotational speed, and angle of incidence. They want to use robust, statistically defensible math models for this propeller performance. And the anticipated aerodynamic performance models we know are going to require higher order terms and interactions. Regression models were desired for use in flight simulators, and they wanted to have some bounds on prediction. So we want to develop a general testing approach for tilt-rotor characterization. So let's talk a little bit about this aircraft's what we call operational envelope. It's probably most easily seen by the little cartoon at the bottom here. The vehicle is going to take off. Both its wings will be oriented 90 degrees to the ground. So it's in helicopter mode, if you will. It be able to hover, take off, clear any obstacles like buildings in the city, and then transition, meaning tilt the wings forward until it gets to forward flight. So basically 0 ground velocity to up to, say, 150 miles an hour in forward flight, and then reverse that and land hovering once again. So as you can tell, the propellers are going through a very large range of angles. And nominally it's 0 to 90 degrees. Both wings tilt. So here's the aircraft fuselage in gray. You can see the 2 red wings. Black dot is where they pivot. The motors sit out here on stalks so the propellers can fold, and they move with the wing. So when you set this angle of incidence, you're setting the angle that the propeller is with respect to the flow. Okay. So hover is going to be somewhere around 82 to 85 degrees. Transitioning is going to occur at a much lower angle of attack, probably down in the 45 to 20 range. And finally, forward flight is about 0 degrees. So what are the metrics we look at for performance measurement? Well, we choose non-dimensional coefficients for measuring our forces and moments. So they're shown over here. It's not extremely important you understand everything in those equations, but the takeaway here is by non-dimensionalizing the forces and moments, we're able to compare to measurements from other facilities. We're able to scale these values for different velocities, etc. So 3 forces and 3 moments are measured. So you think about 3 dimensions. You have a force in the X, the Y, and the Z direction. You're also going to have a moment, or a torque, if you want to call it that, about each one of those axes as well. Okay, so 3 forces and 3 moments. Now the propeller is going to be at an angle of incidence, which is shown here as alpha I, to the oncoming free stream velocity. This experiment was performed at the Old Dominion University low-speed wind tunnel. So this is not the one that was talked about in my bio, but this is a small facility on campus at ODU where we do these types of experiments. And just to talk a little bit about how a wind tunnel works, think of it as a closed duct. Okay, so here we have a racetrack of air moving around in a closed circuit driven by a fan. It changes in cross-sectional area primarily to save energy in the return of the air to the fan, and then also to allow the flow to slow, be conditioned by breaking the flow into little eddies and reducing the turbulence, then going through some area contractions where we then have 2 test sections. The low speed one is a larger one here, and then a high speed one. And these were really well poised for the experiment because the hover to low speed transition could be done here, and then beyond to the high speed forward flight, we could get up to the speeds we needed here. So it was actually very well poised for the project. You can see the 2 pictures that I showed at the beginning of the talk, and those are the test stands that go in the various test sections. Okay, data is collected in both sections. That is going to be possible through using a rig that looks like this and is movable on different supports. The support is designed to be robust to vibrations with that rotor spinning, any kind of minor imbalance and you get some vibration, so it has to be robust to that. We did originally have a servo that drove the motor around at various angles of incidence, but we had some trouble with that and decided to go back to a simple sector that allowed us to set the angle of attack by locking a pin in place. We measured RPM using a retroreflective laser diode, and the motor propeller system is the same as the one used on the actual vehicle. So that's mounted to the front here. Issues with motor getting hot and influencing the bias in the load cell, which is positioned here. And so we have some insulative support gear here, a fiberglass spool. Okay, this is all powered by a large DC power supply. The force and moment data is measured by a strain gauge load cell, which sits here in the purple area. And the forces and moments are measured in the plane of the propeller. Okay, a few more details. Here's the model. This is actually the model from the upstream side in the NASA Langley 12-foot wind tunnel. So they were working on the full model with propellers. We were working on the propeller and motor model only. This gives you a little more idea of the scale with the folks standing here, and also the number of props and how they lie on the vehicle. We were testing 3, 4, 5, and 6 blade propellers, and here's a 5 blade here. Shows you how they work. So hub in the center here, hinge pins at the root of the hub. Each blade can fold back, and if you look at the design over here, you can envision the blades folding down and laying flat against the protrusion that sticks out in the front of the wing. So we were able to collect data using a custom-written LabVIEW software routine. If there are any engineers out there, a lot of us are using LabVIEW these days, very easy to use. We were able to record and monitor RPM, test section temperature, velocity, motor temperature, motor current and voltage, and then of course all the desirable force and moment coefficients, monitor everything in real time, and save files of given sample length. So for the low speed design, the lowest velocity up to about 12 meters per second, we looked at using that low speed test section. Test objective here then was, first of all, to find out what does the design space look like. And I think unlike some of the experiments that were being showed before me here, those are very expensive experiments. This one is not all that expensive. It's fairly easy to make runs, and the accounting is such that we get to pretty much do what we like in terms of exploratory runs. So the first thing we did was look at what the design space limits looked like. And we also wanted to do some runs to compare to some existing NASA data for the 3 blade props. So 3 factors: tunnel velocity, propeller angle of incidence, and motor RPM, shown in the cartoon right. Factor levels then for the tunnel velocity were from 0 for this first test to 12 meters per second. And we looked at angle of incidence up to 100 degrees in 20-degree increments. And just 1 factor RPM was varied while the other 2 were held constant. Again, we're not using this for model building, we're using it for exploration. Here are some comparisons to the NASA data. They had taken some data in that bigger wind tunnel I showed you with just a bare prop. Their flow quality is not as good as what we have in our small tunnel for the props. And we wanted to look at their data versus ours, and those are these comparative plots. So dark symbols are the NASA data, the X's are the ODU data. You can see where they overlap. And for 2 different facilities, we were very happy with how well this correlated. And this was important because it was a brand new test setup, software, just a whole lot of ways to go wrong. So this gave us a very good feeling going in that everything was working correctly. And I can't stress that enough. If you do an experiment design, get as much information as you can at the start of an experiment to set you up for success. Okay, primary objective here is the accurate prediction of force and moments. And the question that was asked earlier about, when you're looking at a prediction model, is it essentially okay to have variance inflation factors that maybe aren't ideal? I'm going to address that later. Where that really comes into play is when you start using higher order models, because it's really hard to get your VIFs down to the rule of thumb value of under 10. That's difficult to do. And I'll say that from the start, our objective here was prediction. So we were really focusing on our prediction error. And because we couldn't use classical designs, because from our original exploratory runs, we found out right away that we were at least looking at 4th order modeling. So that really lends itself to an optimal approach. And when we're talking about prediction, the natural selection is the I-optimal approach. While we built the design, we decided to look at another order above the order we felt we were going to use. So a little bit of headroom. We decided to build for a 5th order model. And of course, any terms that are not used go into our lack of fit error budget. So that worked out very well in this case. So what we ended up doing was taking velocity from 2 to 12 for the low speed design, angle of incidence from 0 to 100, and RPM from 4,000 to 6,500. And so that's what we learned from our initial exploratory runs. Now we have our factors, we have our levels and limits, we've identified our model order. One of the lessons we learned from the 4-blade SplitPlot was the first one we did was that recirculation effects at high incidence angles and 0 tunnel velocity were actually giving us a lot of trouble. So we had to have some velocity. Couldn't start at 0 inside our closed tunnel. So we had to start at 2, and that's what drove that choice. We also had some constraints on what our power supply could put out when it came to the 5- and 6-blade props. And that was because we had a given wattage for our power supply. We thought we were going to be able to run it at its full voltage, and then we found out that the motors that were given to us could not run at the full voltage, so we didn't have quite the overhead we needed. Why am I mentioning this? This always happens, right? You set out to do something, and somebody throws a curveball at you, and you have to adapt. That happens to us all the time. And a lot of people that are pushing on us to say that their one factor at a time approach is fine are always saying, well, how are you going to adapt? So we are always trying to show that we can adapt. And that's one of the goals here. So here's what that split plot design looked like for the low speed test. I'm showing 3 of the 8 whole plots. So the whole plots show easy to change and hard to change factors. Velocity and RPM are very easy to change from the control panel. Angle of incidence required us to pull a pin out and in and out, go inside the wind tunnel with the flow off and change the angle of incidence. We didn't want to do that for every run, hence the split plot design. Okay. All right. How do you do this in Design Expert? How did we do it, I should say? So we started by choosing optimal design under response surface under the split plot heading in the navigation panel. You can see that on the left. Specify your factors, of course, and whether they're easy or hard to change, and of course your levels. Next, you're going to define the model order. So we could support up to a 5th order model. That's what we wanted to have. We knew that we'd probably go back to a 4th order. And just on the right-hand side, I'm just showing you the flavor of the terms that are going to be involved in the model. So that's just up to 3rd order terms. But those are the kind of terms we wanted. We wanted these mixed terms with the mixed interactions. That was important to us because we could see in our exploratory runs that we're going to be looking at those types of terms. Again, we chose I-optimality with the goal being to minimize the variance of prediction over our design space. We also knew that the whole plot error that was associated with our testing was going to be relatively low because we were able to set the whole plot factor very exactly, all right? And we knew it was very repeatable. So we knew that would be fairly easy to deal with. We left the variance ratio at a conservative value of 1. It was actually about a half when we measured it at the end. So that turned out to be a good planning value to use to give us a little bit of headroom. We added additional whole plots to the recommended number of whole plots. I believe Greg alluded to this in one of his slides too. And it's really important whenever possible to have as many whole plot reps as you can. And so we added the ones we felt we could afford. We had 5 additional model points for increased lack of fit degrees of freedom. And we were able to run the coordinate exchange algorithm for point selection to look at any points in the design space. So this is what those menus look like if you're using Design Expert. So here's what it looks like now in the design space for the 3 factors. This is using the graph columns feature in Design Expert, which I love, because you can look at how it's all set up before you perform the experiment, get a feel for how well points are distributed across the different factors, okay, and make sure that you can hit all the points that you think you can. Okay, specify the 6 responses. That was just a matter of the 3 forces and moments. And then after the design was built, we adjusted the angle of incidence values that could not be achieved to the nearest value. So in hindsight, always good, we should have really used a factor type discrete and specified the discrete values. But there are some reasons we didn't do that. One of them was we thought we were going to be able to vary it continuously in the beginning because of the use of the servo that didn't work out. So anyway, there are a lot of reasons, but it worked out fine. We just had to adjust our set point a little bit, go back and look at our design metrics, and and work with it the way it was, and that worked out fine. Okay, so next thing we do is use evaluation to review design metrics. Again, under the evaluation results tab with a fourth order model chosen, our intended model, and the variance ratio of 1, we can review some of the metrics that we like to talk about. We could talk about power. I noticed Greg was emphasizing power, and it's very important. It's particularly important in design of experiments type designs like factorials, or you're doing screening, and you're very interested in understanding which factor does what. We're in a little different boat here. First of all, we have very complex models, which makes getting very small VIFs difficult. Okay, and second of all, we're mainly interested in our prediction qualities. So we are willing to live with a little bit of variance inflation. And really, it's kind of a necessity when you look at models, like even just looking at the whole plot terms. If you look at B versus B cubed, it's very hard to get all that correlation out just because of the way you set your factors. So we live with that. And for this design, then we had 3 whole plot error degrees of freedom and 23 subplot error degrees of freedom. Could have probably used a few more whole plot error degrees of freedom looking back at this, although the models work very well after the analysis. We always look at the distribution of prediction variance. So under the evaluation graphs tab, again, you can find that in Design Expert, and you can see how good a job the I-optimal routine did at getting us a really even distribution of prediction variance over this area. So here we're looking at velocity versus angle of incidence, and you can see other individual factors shown here, and you can see that it looks really nice over the whole design space. Okay, well, this is my favorite metric when I'm comparing designs, the fraction of design space graph. If the goal is characterization, the emphasis is on producing a fitted surface as precisely as possible. And for the 2 main areas I work in, which includes calibration, where we're looking at instrument calibration, we're trying to reduce our confidence intervals, right, as much as we can for prediction. And then also in aerodynamic characterization, where we're really doing the same thing. We're building a model. We are trying to understand interactions. We are typically not looking for factors like you would in a screening design, right, where you'd say, well, let's throw in landing gear off or on. It probably doesn't have effect. We know it has an effect, okay? So we know all the factors that are involved in our design are going to be part of our characterization. It's just a matter of understanding how they're part of it. So our primary goal then is really to look at our characterization prediction error. And this fraction of design space tool is a great way to go. So if you go into that tool in Design Expert, looking at the definitions, delta will be your interval half width. Okay, so here I'm looking at the standard error of the mean. Sigma is your population standard deviation estimate. We typically don't know that for the kind of designs we're working with, so we leave that at unity. And then we're going to look at alpha, our level of significance, as per usual. We're often using 95%. And for this particular example, then we're looking at 95% of the design space having a mean response with a confidence interval half width less than or equal to 2.31. And since we're using a standard deviation of 1 here, you can think of that as 2.3 standard deviations from the mean. All right, so that's our interpretation of this FDS graph. Okay, so we conduct experiment, we're analyzing it now, and we use the analysis of variance with a restricted estimated maximum likelihood, or REML. We started with a quartic model and used backward elimination. The models were highly nonlinear as expected, and here is a portion of that model shown on the right. Okay, so this gives you an idea of the type of terms. So all these terms are either in here for hierarchy or they are significant. And in fact, just looking down through the p-values here, there are very few that are in here for hierarchy. everything is significant except, I guess, one term in here. So you get an idea of the complexity of the models. Fit statistics then for R squared and R squared adjusted, just thinking about what percentage of variation in the response is explained by the model. You can see the typical low noise environment that we work in. The R squared values are very high. And this is for wind tunnel testing. In the calibration environment, these values are low. We like them even better for R squared. So it's a little different than what somebody might be working on in, say, chemical processing or manufacturing or other disciplines, right? Or if you even dare to say go back to somebody like Fisher, I can't imagine he's getting these kind of R squareds for crop testing. So for us, we have to really judge these carefully. And actually, if we're looking at one that is going to require us to look a little closer, we would look at something like CFY. And this response, the force in the Y direction and out of plane force on the propeller, was actually very, very low. So signal to noise ratio is extremely low. And so the model wasn't great. And it really didn't matter all that much because the mean value was so low, it wasn't of great interest to the aerodynamicists in the subsequent modeling using the propeller. So that's some basic fit statistics then for all of the different props. And of course, this experiment that I showed was done for each individual prop, the 3, the 4, the 5, and the 6 blade. We of course go in and check our residuals, confirm normality, independence, constant variance. And we had a few outliers here and there, and we had enough runs that we could take out a few points. So we didn't have any great trouble with that. All right, let's look at some sample results now. So this is thrust coefficient. You can think of this as the forward vector of force coming from the propeller. This is what pulls the aircraft forward, right? And it opposes the drag force. And I mention that because a typical response that we see with velocity for thrust is as the velocity of the aircraft increases, which we see along the x-axis of this plot, the thrust starts to go down because as the propeller moves through the air faster, it generates less thrust, and the drag, on the other hand, continues to increase. Okay, so at some point, the thrust balances the drag. There's no more thrust available, and you're over to the right here somewhere on this plot. Okay, and that's going to be the max speed that the aircraft can achieve. So I think it's pretty easy to understand that as velocity picks up, thrust goes down. At 6,500 RPM, we have more thrust available than we do at 4,000. Makes sense. Spin the prop faster, you get more thrust, right? So that's what we're seeing here. It's a classic interaction, right? Because at 4,000, we see that the response is a different slope than we see at 6,000 or 6,500. So that's the 4-blade prop. Similar things with the 5-blade prop, although it makes more nominal thrust. So we can see that here. And these experiments are necessary to provide the detail and to quantify the precision that you can't get with a theoretical approach. So now let's take, instead of a forward flight condition like we saw there where the angle of incidence was 0, let's now go to 60 degrees. So now the prop is 60 degrees inclined to the flow direction. It's an interesting point. Funny things happen there. Now we see that, remember that two-factor interaction we saw here, it's really kind of disappeared. Now there's very little difference between 4,000 and 6,500 in terms of thrust coefficient, right? And we see that for the 4-blade as well as the 5-blade. The interaction effect is gone. And finding that point is really important for flight simulation. So these trends are predicted by theory, but it's hard to grab that critical point without an experiment. And this particular result is even more important, maybe a little complicated to look at, so I'll try and describe it. Here again is the vehicle. In order to achieve a trim condition, pitching moment has to go to 0 in the overall aircraft. Now we're looking at pitching moment only from the propeller. So we're looking at the contribution from one prop, and there's one at the front and one at the rear. In fact, there are 4 at the front and 4 at the rear. And so we're interested in that contribution to pitching moment in the overall simulation in order to reach a trim condition, meaning that pitching moment is 0. Otherwise, the aircraft is accelerating, it's moving in terms of moving around its center of gravity. So here are the pitching moment responses then for all 4 of the blades tested. And you can see, let's look at the 4 blade here. You can see that as this angle of incidence gets up close to 80 degrees and beyond, that suddenly this relatively benign surface sweeps up dramatically, right? Pitching moment increases dramatically. And that happens not at the low speed, but at the higher speeds. So that's of great importance to model, right? To understanding things like how to come up with a simulator for our vehicle and to do things like predict how well, what sort of range we have, how easy it is to control, how big a control surface should be. All these things factor in from this test. All right. So that was the low speed test. I'll now just go a little further and talk about the high speed test. A little less detail, but what we did with the high speed test is limited the angle of incidence from 0 to 20 degrees. Because if you're at high speed, you're no longer at this high incidence angle. You're either about to go in the forward flight condition or you are in the forward flight condition, one of the two, okay? So you're in between that 0 to 20 degrees. A windmill condition occurs when you get to a velocity where you can no longer make thrust. It's called windmill because if you keep increasing the velocity, you actually get negative thrust. So you actually are drawing energy out of the flow like a windmill would. And you can see how that plays out as a function of RPM by looking at this plot from the graph columns. This is where we ended up. Okay, so this borderline, which is shown in red, is where thrust is no longer being made. And we had to do that by doing some exploratory runs. We then put the constraint into our design and built our I-optimal design with this constraint in place. Very nice because using the I-optimal routine, we're able to get the best prediction variance distribution over this odd-shaped space, right? Which is our goal. So if you're interested in how to lay out the constraint, it's shown here, and it's pretty well documented rather in the design expert help files. So we're using that same I-optimal design approach, but we're now going to do an aggregate test that's going to involve all 4 of the propellers at the same time. Now we could actually support that because the angle of incidence was not from 0 to 100, but rather 0 to 20. And it made it fairly easy to do that in our high-speed test section. Blade numbers now added. It's a categorical factor. So you can see here's our list of factors: velocity, angle of incidence, and RPM as before, but now with blade count over 4 levels, and it's a categorical factor. It's hard to change because you need to stop the tunnel, unbolt the propeller, put a new propeller on every time that's changed. So we left that as a hard to change. Angle of incidence is still set manually, so it's hard to change. And then velocity and RPM are both easy to change. Okay, so that's a starting point. And here's the 4 of the 17 hole plots from the test. So you can see our 2 easy to change columns and our 2 hard to change. And reviewing the design metrics again in evaluation, now we have 5 whole plot error degrees of freedom. Okay, a little better than our first design. 8 subplot error degrees of freedom. And that's fewer degrees of freedom than the previous design, but as we saw in the previous design, we had many more than we needed. And we found that model order went down, it didn't go up, so we didn't need that extra overhead. And there are some issues with correlation, but it's fairly small by our standards. You can see over here, we have some terms that are high. And we had the same objectives. The emphasis was going to be on prediction, okay? So again, using evaluation, looking at the graph section, here is what the distribution of prediction variance looks like for the constrained space. And again, the I-optimal routine did a really nice job of keeping that prediction variance fairly uniform across the space. Okay, analysis was done in the same fashion using analysis of variance with REML. We got estimates again of the variance components, which I've shown at the bottom here. And once again, we can see whole plot error was relatively small compared to subplot error. And here's what the models look like, not quite as complicated as before, and they were limited to cubics. Okay, some more results. We see now we can compare the props directly, and that was extremely useful. So each one of these colored curves represents a propeller's performance. Again, we're looking at thrust performance here. This is at 6,000 RPM. Again, the family of propeller blades are shown here. And you'll note on the bottom two graphs, we're looking at the torque required to spin the propeller. So you can see as the thrust goes down, on the upper curves, the torque requirements are going to go down as well. They're negative values, that just has to do with the sign, but the actual magnitude goes down as we go up in speed. Notice that the green line crosses the red line. That's the 4-blade, 3-blade. So we found some anomalies, and the 3-blade showed this minor increase, and we weren't sure exactly what that meant. Okay, we also saw that in other data. So in the pitching moment responses, even if you know nothing about this, to use Greg's brass analogy here, even if you're a manager, I'll say, okay, you can look at these colored pretty plots and say, hey, one of them's different, right? So here's the 3-blade, and you can see that the pitching moment is falling off with angle of incidence at the high values, whereas with the 4 and the 5 and the 6, that's not happening. So there's something going on there, and we think we've tracked it back to the folding hinge point on the props. We believe that the 3-blade hinge setup was too tight, not allowing enough motion. So again, really nice details in experimental results, and you can pick them off because the plotting routines are nice, and Design Expert allows you to find these little anomalies. So in conclusion, that the SplitPlot design approach gave us a practical experiment efficiency. We still got to use our necessary randomization. We still were able to use our I-optimal routines to minimize our variance. The hard to change factor changes, as I mentioned, were very repeatable, and hence the whole plot variance was low. And we knew that going in, and it proved itself in the results. So I only showed a very small portion of the results, hopefully some that you could relate to a little bit. The complete simulation database was created from these 5 tests, which included the individual prop tests at low speed and then one aggregate high-speed test for all of them. And this database is going to be used for a full flight vehicle simulation. So the project really showcased the important tools for aerospace engineers who have, I will say, traditionally been reluctant to use DOE RSM. There are a few instances of its use in the 60s, and then there's not much until the 90s when you start seeing some use at NASA Langley. And that since then is really when we've been able to build some momentum for use of these superior methods for experimentation. Design Expert software is used throughout design creation, evaluation, analysis, and model building, and also model presentation and interpretation. And it really is my go-to software. I thoroughly enjoy using it, and I do an awful lot of teaching, and I find it's very easy to teach with as well, because it's easy to understand for the beginners. All right, well, we'll take questions.
All right, does the audience have any questions they want to ask? We don't have any typed in at the moment.
Okay.
Yeah, I love personally. Before I went into industrial engineering, I spent 1 semester in aerospace engineering, and so I always love these talks about the applications in this field. It's fascinating to see all of all the different ways you can apply this. Greg Perrine asks, he says, you may have mentioned this, but did you walk through what an OFAT approach would be for these experiments and compared the power differences, pros, cons, what a design offers you versus OFAT, etc.?
Yeah, I would say, Greg, one of the things that you have to be careful of when you're comparing an OFAT to a formally designed experiment is that you can get a power number, but I think you're violating a lot of the assumptions that go into power. And if you want to compare the designs directly, you can do it. You can do it in Design Expert. We did not do that. We only use OFAT for doing some exploratory runs when it's easy to reach the limits of an experimental design region. I'm a firm believer in randomization wherever possible, and I even showed that today, how you can identify problems by using fully randomized designs, or today I showed you how to use SplitPlot designs, which use as much randomization as possible and still afford us a lot of what we can get from an OFAT in terms of efficiency.
Yeah, I agree in using OFAT for those range finding kind of, I tell people to use it initially to kind of figure out the capability in each of the factors, but then jump into the designed experiments. We do have Wolfgang from Germany asks, did those props have all the same velocity?
Same velocity. Well, if you're following the talk, the wind tunnel velocity was varied as a factor, and the RPM was varied as a factor as well. Okay, so those are two of our factors. So if you're looking, let's go back here. So for instance, here we're looking at pitching moment from the 4 different propellers. Here's the range of velocities that was tested over the high-speed testing. So it goes from 12 to 30. Okay, this is a particular result where all of the propellers are turned at 6,000 RPM. Okay, so rotational speed's the same for all these. Of course, you can change that within the software. You can go in and for the results, you can dial in any RPM you like, but I just chose one to be representative.
And related, was the issue with the 3-blade related to the blade size?
Not to the size, but let me see if I can go back real quickly here and just kind of point to the problem. So if you look at the blades, here are the blades, right? At the root of each blade, you can see there's a little screw with it's actually a locking nut, okay? So it turns out if that torque isn't exactly right, too much pinching occurs between the plates, and the blade, if it doesn't move like the other blades do, if you have one that's off, or even if you tighten all three too much, you completely change the performance of the propeller. And it doesn't happen over the whole range. It happens at certain points. And that's what I showed in that slide that had the anomaly with the 3-blade.
Okay. And here's a question about the SplitPlot structure and setting that up. Femi would like to know, how do you determine your hard to change versus your easy to change factors? What informs that choice?
Oh yeah, it is literally the way it's described. What is hard to change and what is easy to change? And I'll illustrate that with this piece of hardware. So here is the motor with the propeller on the front. This is the actual propulsor, and then that's forward of where we're doing the measurement of the forces and moments. So the motor is controlled by a little knob we can twiddle to bring the RPM to any desired setting. That's easy to change, okay? So that's RPM. The velocity of the wind tunnel is the same thing. You can twist a knob and the velocity changes very quickly, also easy to change. The angle of incidence, which means raising the propeller up against the airstream at an angle, occurs by pulling a pin out here, physically moving this forward, and then putting the pin in at the new angular increment. So that's hard to change because we have to stop the wind tunnel crawl inside it, pull the pin, set the new angle, replace the pin, and start testing again. So we try not to do that. We use that as a hard to change factor.
Yeah, I agree that it's pretty descriptive in what defines hard to change versus easy to change.
Mm-hmm.
Michael Morrow, his comment question says, your models had many hard to change by easy to change interactions. They have a lot of degrees of freedom. Is this common? And if so, does this make you feel better about having low degrees of freedom for the whole plots, especially since your variance ratio is low?
Wow. Okay.
Yeah,
I
that's
don't
a
know.
lot.
That's a good question. I'm not really sure if I understand what the question is.
Well, let's start with the first part. So you had a
Yeah.
lot of interactions between hard to change and easy to change. That has
Yep.
a lot of degrees of freedom. Is that common in your experience?
It is common. Absolutely
Mhm.
common. Yes.
Okay. So does that help to make up for having the low degrees of freedom for the whole plots? And I mean, I can throw in it helps because it drags those factors along in the modeling if
Right.
you keep hierarchy. So
Yeah, that's all I could think of. I don't know. I should probably know more about does it change anything else? It's a good question. I
mhm.
couldn't say more than that, really.
Yeah, I find that in our examples too, is that you can kind of get by with the um, low ability to test those whole plot factors as when you have when you can expect that there's going to be interactions with them, because the interactions will just pull along the whole plot main effects into
To
the
the hierarchy. Yeah,
yeah.
I see what you're saying, because the subplot error is tested against the interactions between whole plot, subplot factors. I guess that's what the question's getting at. Sorry for
Yeah,
being slow. Yeah, okay.
yeah,
Yeah, that
yeah.
would make you feel better. You're right.